full scale or ground, VSS. Okay, either one of these two. Okay, so this is the circuit. And here this switch, which is shown by a single pole double through switch, is connected to ground if corresponding bit, we have 3 bits, A, B, C. So therefore, for example, for A, if A is equal to 0, therefore you will have connection to ground. I show it by this symbol. If A is equal to 1, you will have connection to V full scale. This is same for B and C. And A is your LSB, B is intermediate bit, and C is MSB in general. Okay, so therefore, eventually from left to right, you will have B0, B1, B2. So this is your LSB now, which is on the left. So this is A, this is B, this is C. Because it is opposite case, I'm just showing it in this way. Doesn't matter. So because what I have given is independent of the order of bits. You just show for 000 input V out is equal to V full scale, and for all 1 input code V out is equal to V full scale by 8. By the way, this is reverse in the sense that actually when you have 000, your real input is 111. And when you have 111, your real input is 000. Means that these bits are actually opposite or complement of your bits. Or you can change this order. That would be same. But because 0 is equivalent with 0, 1 is equal to V full scale, I don't change it here. I just put a bar here. Therefore, don't be surprised why for 0 you get V full scale, for all 1 you will get V full scale by 8. So the point is, when you have 000, means all inputs are connected to ground, you will get V full scale. This corresponds to 111, and these bits are complement of input bits. So the only thing here you see is there is a shift of V full scale by 8 to right. Means that for all 0 you will get V full scale by 8 instead of 0. For all 1 you will get V full scale. That is because we don't have any negative voltage here. But still your complete range is covered. And to use this analysis, this is good to always simplify the circuit. Therefore, it makes it very easy if you use this. Always when you have a ladder, when you want to analyze a ladder, for example, suppose for all zeros, you will get something like this. Right? So always you start, draw the equivalent thevenin of the circuit. Start from left, come to right. If you have some points which are connected to V full scale, therefore not only equivalent resistor, equivalent open circuit voltage also needs to be included. Therefore, always you will have a circuit like this. This is your R equivalent. This is your V equivalent. Then analysis will be very simple. So now you do it for two cases. Okay, this lecture, now we have around 1 hour time to look at some of the issues with the offset and then how we can compensate for offset. Again, we are coming back, it's better. Now it's a variation again. Again, you know now some architectures. Now we will come back again to non-idealities. Okay, so this lecture, mostly we will focus on offset compensation and even effect of offset voltage after offset compensation. And then now you know charge redistribution and charge-based DAC. Now we will use it. We'll come back to STAR ADC and then now we will look at making a STAR ADC using this charge-based DAC. Okay. So this lecture I will write. Last lecture we were here where we have this binary weighted resistor array. Okay. Binary weighted resistor, capacitor array. And this is just a passive network. And we put an additional capacitor over here, which is C, to make denominator 2 to the power n into C. And therefore, that was the reason behind putting this additional resistor. And therefore, when all are 1, we will get 2 to the power n minus 1 divided by 2 to the power n. So now the problem is it is very sensitive to parasitic capacitances exist at the output, right? So this creates a lot of problem. Therefore, we add an op-amp so that we can make this node as a virtual ground. And then we put a capacitor in the feedback path of the op-amp. And therefore, we will get a better control of effect of parasitic capacitance because all of them will be connected to a virtual ground. But now as soon as you add one op-amp, then you need to compensate for op-amp offset. Okay, so that now we will add an op-amp and then we will compensate for op-amp offset. Now using techniques that we learned in the previous lectures. So first of all, suppose I have this same ladder. These are capacitors. Okay, so I shift this one capacitor over here. So this is feedback capacitor. And therefore here I will have only binary weighted capacitor. That additional C now has been shifted as to the feedback path. And then finally 2 to the power n minus 1 C. And here you will have these switches which will be controlled by input code. So one side is V full scale and one side is VSS level. Okay, and they are controlled by the by bits. Therefore, this is B0, LSB on the right, and V n minus 1, MSB on the left. So it's the same ladder. Only what we are doing is we are just connecting a capacitor, and then now making this output node, which was already output voltage. Now it is a virtual ground. Therefore, now all internal nodes, as you can see, except output voltage, now they are being connected either to ground, V full scale, and virtual ground. So this will help to avoid effect of parasitic capacitances unless we have parasitic capacitances which may be like parallel between these two nodes. I mean, if this happens, then we cannot do anything with that. That is a part of capacitor. Okay, so now, but if there are capacitances between this node and ground or between this node and V full scale, so those will get shorted. Therefore, it doesn't create any problem. So now it's the same as before. So output voltage. Eventually what happens is that according to your connection to V full scale and ground, you will get some charge on these capacitors which will be eventually shifted to CF, and therefore this is like an inverting amplifier. So the same relation is valid. So charge which is stored on these capacitors is a function of input code according to total charge, and this total charge will be also transferred to CF. Therefore, total charge which is Q, in general equal to CV, we write it here. So I is equal to 0 to n minus 1. It is Bi, which is input bit for input bit to the power I into C into V full scale. This is V out. This is total charge which is also transferred to CF. Therefore, divided by CF will give you V out. Only there is a small point here. You notice when there is a capacitor over here and it's getting charged, therefore charge will get transferred. In fact, this capacitor will get charged in this direction, right? And this charge also will get transferred to the output in the same direction. Therefore, your V out actually may have a negative value if we just assume like this. So therefore, accordingly, whether you put here plus V full scale or minus V full scale, here you will get at least minus or plus. That's why we put it here. And then if we want to get same relation that we had previously, then we should choose CF equal to 2 to the power n into C to give us exactly same value. And therefore, it will get simplified by this range. Okay, so this is if offset voltage of op-amp is equal to 0, input offset voltage. But if input offset voltage is not 0, eventually everywhere this charge won't be simply Q won't be simply C into V full scale or 2C into V full scale. Eventually it will be C into V full scale minus V offset. Therefore, everywhere you will have a new relation. So V out, considering the input offset voltage. Now, there will be two components. One will be here because your output voltage is considered to be voltage across CF plus V offset, right? So therefore, you will have one term which is V offset in here, and you will have another term which has V offset inside the fraction. So therefore, this will be now new relation for V out. So one part of it seems to be something like a gain error term which appears here in the fraction, and the term which appears on the left seems to be offset error. Therefore, we can compensate for both of them. So first we will go with main compensation, which is offset compensation or offset error compensation. So therefore to do that, then we need to have a two-phase conversion. Okay, so this was a parallel conversion. It seems in one phase it can be done. But we need to put one phase for offset compensation. Therefore we will have two phases. Therefore phase 1 for offset compensation and reset, and phase 2 for conversion. Okay. So now in phase 1, which is the reset phase, as well as compensation. So we just add some switches, right? This is what we need to do. So what are added switches? For example, one is here. The reason is because now we want to remove this CF and make op-amp in unity gain feedback. I put offset because it shows that they are added because of offset. And then here was the capacitor array. Binary weighted. Here are those switches. I don't redraw. You know what we are saying. Just I want to show what has been added. And then finally you will have one switch over here to reset all capacitors. Therefore this is S3 for reset. Okay, so we have actually 3 or 4 switches, eventually 4 switches. Okay, so then in offset or reset phase, which is phase 1. Phase 1. So therefore S1 offset is open. Oh, we need one more switch also to keep transistor in, to keep op-amp in unity gain feedback mode. So there is one more switch over here. So I tell you one thing else also can be done. S5 offset. Actually, one thing you can do, you can remove S1 and S4 for offset. The reason is because now you will be able to discharge CF completely. However, if you do that, then you won't be able to store offset on CF. The reason we put this S1 and S4 is to connect CF to ground. Therefore, CF will come over here at the negative terminal of op-amp. And because it is at the negative terminal, therefore we would be able to store offset on this capacitor. If we put it in parallel to S5, then it will get discharged completely, which is not what we wanted. So what we want to do is that we want actually to store offset on CF, so that this offset will be removed from V out. So now, therefore, we will need this S5. So S4 offset will be closed, and S5 for offset is closed. S2 again is because of offset is open. Eventually we need 4 additional switches for controlling offset. And S3 of course is for reset, therefore we keep S3 also closed. So bottom plate is connected to ground. Now what will happen? Equivalent circuit now will be like right side will be disconnected from left side. Therefore we will have in this phase only one op amp with capacitor CF at the input and with unity gain feedback. This is S5 offset. Okay, so because it is in unity gain feedback, we saw before the out was V offset into gain, op amp gain, A plus 1, right? This op amp has gain of A. A is positive. So therefore, if A is enough large, this can be almost V offset. So therefore, we need to have enough high gain op amp so that the error we get here should not be more than half LSB. So we will use a very high gain, enough gain op amp so that we will get almost V offset. In fact, error is V offset upon A, 1 plus A. We want to make it enough smaller than half LSB. This is the condition, first condition for gain of op amp. And then we make it enough smaller so that the eventually offset will get compensated. So now because output is this V offset almost, that will be stored on capacitor CF, which is going to be kept in the feedback mode. So, and the direction will be like this, right? Now you can see how it is getting compensated. Because here you have, see, as soon as, because this node which is connected to ground will be back connected to output afterwards. Therefore, your output will be V offset plus something minus V offset because this is connected to output. And therefore, offset gets compensated. So, this is only in the offset compensation phase and that is the only difference. Then, in the other phase, it is same as before. I mean, the equivalent circuit will be same as here. Only what will happen here, okay, I have used V offset in. So, everywhere I use V offset in. Okay, so now when it is connected, you have something like this. V offset plus other things. And V out is minus this voltage, right? Therefore, whatever you had in the form of V offset, now you will have a minus V offset V in. V offset in, it will get compensated. So, what remains only is this factor, which is eventually V offset appearing as a error in the gain. Okay. So, do you want me to prove it is a gain error or will you do? So, after storing V offset on CF, V offset in on CF. V out is V offset minus V offset. This is almost because we approximated A to be very large. Minus plus that. No, it's here. Okay, I will keep it. Pi C 2 to the power IC minus plus V full scale plus V offset. If CF is 2 to the power NC. So this term will get cancelled. What remains is second term. So do you want me to prove it is gain error? So what I mean is that eventually if this offset is constant, It doesn't change with temperature or input. Everything is constant, this offset voltage across the entire conversion cycle. Then you can do it only once and then DAC can operate, or you can do it once a while. However, if this offset changes, therefore you need to compensate every cycle, which is very impractical because you need to have one offset compensation phase every conversion cycle, which will slow down the operating frequency. And the whole motivation behind using a parallel conversion will get affected. But this is, if this, you can approximate this offset to be almost constant, therefore you can do it once and then all the time it will operate properly. So what remains is only gain conversion, gain this in fact error, and that gain error again will be easily compensated afterwards. So we don't compensate gain error here. It can be compensated at a digital level, I mean by the software, or at the so I don't okay, so I will write it. Proof, in fact, so after offset compensation, still effect of the offset is there. So offset error is equal to 0. Remaining effect is gain error. But only this needs to be proved. See, intuitively you can see it is gain error. The reason is because, so if you look at this term, this is the real term, what you expect, and then additional term is bi to the power I CV offset, and this term which is added is exactly proportional to the gain you have at a particular code. Therefore, you have an amount of error for every code which is equal to, in fact, error, relative error, will be V offset upon V full scale. What I did is just I factors V full scale, and therefore you will have 1 minus V offset upon V full scale. This coefficient also is common for both, therefore relative error eventually is V offset V upon V full scale. Relative error means that the amount of voltage you get with respect to the amount of voltage you have, amount of error you get with respect to the amount of voltage you wanted to. So it is constant, but still we can prove it is really gain error only. So for example, one way would be, suppose if you have gain error, one way you can do is that you can just put an amplifier which will correct for the gain error at the end, after that, right? And if your gain error is in such a way your final gain is less than 1 for that. If it is more than, you will attenuate it a little. So this is one way which can be done without any software. But the gain of that amplifier or attenuator need to be controlled properly. Otherwise that itself will add to error. So you know this gain error is V out upon LSB size for all 1 minus V out upon V LSB size for all zeros minus 2 to the power n minus 1. So in our case, what is the error we are getting? at a particular code I. This is gain error with respect to the final code, and then we can scale it for every sample. For example, for I equal to n minus 1. That was for ADC. This is for that. Okay. See, amount of error in general. This is error. I'm not talking about definition of gain error, just I will replace it. It is this. With a negative sign. And then we need to scale it to 1 LSB, therefore it will be 2 to the power n upon V full scale. Right? This is now in LSB units. I just divided it by V full scale by 2 to the power n. So therefore error for this, which will be in fact gain error. Okay, gain error is minus this also. Like, okay, so just I will error at I equal to n to the power minus 1. This will be 2 to the power n minus 1. Yeah, it's summation of all of them when all are 1. Into V offset upon V full scale. This is in LSB units. Therefore, gain error is this error and of course for 0. So V out was for this particular case will be 2 to the power n minus 1 upon 2 to the power n. This is in V full scale. Then we divide it by LSB size, therefore it will be 2 to the power n minus 1 V offset upon V full scale minus 2 to the power n minus 1. So what I did is V out for all 1 will be this, V out for all zeros, this term will be 0 eventually. Okay, for all zeros I have not written. This is for all 1 minus this term minus for all zeros. For all zeros, this term will be 0. Therefore, eventually we don't have anything. So eventually doesn't have any effect. Fine. So therefore, these two also will get cancelled, and this is amount of gain error. 2 to the power n minus 1 V offset upon V full scale. So if V offset is 0, V gain error is 0. Is it correct? Okay. In the error equation. This one. So this is 0. One plus, yeah. No, that is overall offset. No, that is the overall shift. You have an overall shift and then you are bringing it back to 0. But still you may have gain error. Suppose this is code. Say this is 000, this is 001, this is 010. So you are here and then here you will go to the next level. And so on. So now what we did is we shifted this point to 0. Therefore now we have this point and then 001 here and then 010 over here. So now if you have gain error, for example, you may get, because that is related to what you have at the end for final sample, which is all 1, say 111, and then you connect that particular point to 0. So again, this is 000 and this is all 1. Now it's here and then in all 1 your output is something like V111 and this is 0. Now we are connecting these two. And then suppose this was supposed to be something else. So now you have gain error. So this was desired and this is in fact desired gain, slope of this line, and this is real gain. So what we are doing is that we are making the code corresponding to this, which is eventually 2 to the power n minus 1 multiplied by LSB size minus 0 minus 2 to the power n minus 1 LSB size. That is the slope. Yeah, we are not looking at the absolute value. We are looking at the gain. Means that this value, this is expected to be 2 to the power n minus 1 LSB size. And this already we have compensated. Therefore, when you plot this line, you will reach to 0. If it was not compensated, you had something like this. Then when you would have connected, you would get something, a line like this. Then it was not reaching to 0. So first we compensate for offset so that we will get exactly this first point on 0. Then now we will look at the slope of line which is passing through 0. So this is supposed to be 2 to the power n minus 1 LSP, but then it is less or more according to the polarity of offset. Yeah, which is here also is shown like it is 2 to the power n minus 1 LSP size multiplied by V full scale upon 2 to the power n. We normalize it to V full scale to LSP, therefore it will be 2 to the power n minus 1 only. And then for this will be the deviation. So therefore deviation essentially will get that V offset upon V full scale into 2 to the power n minus 1. But you can correct it easily because now you are scaling at all values, and interestingly your error also is getting scaled with the code. Therefore finally you will get a 0 gain error, and then you don't have any other. In fact, what I want to say that this effect of remaining effect of offset is only gain error. There is no distortion associated with it as long as offset remains constant. So therefore how we compensate? So gain error compensation. For any, for example, sample I, what we should do is that we have gain error, scale it by the value of corresponding analog value of this code, which will be I from 0 to, okay, here I should use something else. M equal to 0 to I, Bm, to the power m, divided by 2 to the power n minus 1. I will write it here. This is actually this Bm is equal to 1, which corresponds to Iumin code. For example, here is I equal to 0, I is equal to 1, I is equal to 2, I is equal to 3, and so on. So for example, here is 0, this is 1, this is 2, no, actually it should be B. Bm is nothing. This means that eventually this summation m from 0 to I Bm to the power m is one of these values converted to decimal divided to the power n minus 1. This will be multiplied by gain error. This means that we are scaling. See, this is gain error at all 1. This is gain error in another code. See, it is getting scaled as we are moving towards 0. Therefore, we are multiplying by this value. We had one example from this gain error correction before. So just we are scaling that gain error. So after gain error compensation, so therefore now this will get multiplied by gain error, and gain error was this value. So for simplicity, I put that decimal value equal to j. Therefore, j will be, for example, 0, 1, 2 to 2 to the power n minus 1. Therefore, gain error compensation will be gain error into J divided by 2 to the power n minus. For every particular decimal value of J which corresponds to a particular code. So output voltage was for every code. Therefore, for the corresponding J, in fact will be minus plus after gain error compensation. We will have same value, and then now what we are adding is this term, which is J upon 2 to the power n minus 1 multiplied by V offset upon V full scale. This was versus LSV units. If you want to get LSV versus absolute value, like here, we should multiply by LSV size. Therefore, now these two terms will get cancelled, and that is the reason the out after gain error compensation is equal to VI 2 to the power I V full scale upon 2 to the power. So therefore, if after all the whole story is if op-amp offset is constant, there will be offset gain error and offset error, and both can be compensated. Even if you don't compensate for gain error, after all what you will get at the output will be only a scale version of signal. It's just you have multiplied, your ADC has multiplied your signal by some gain. But it has not distorted because all samples are getting scaled by the same value. So eventually means that you don't have any kind of distortion. So that is the reason this offset compensation is very important. Phase in all ADCs and DACs. Where? Oh, sorry, yeah. You tell me, I will correct it. This gain error was correct? V offset upon V full scale. This is in LSV units, right? This was in LSV units, right? No, here I have not multiplied. Because offset error was, it's here. Offset error eventually is this summation offset upon C, and this will be 2 to the power n. And now for this particular I equal to n minus 1, it will be 2 to the power n minus 1 V offset. Okay, here I have multiplied. Okay. Okay, so it is in LSB units. Fine. So this is gain error. And then I wrote it versus the decimal values like here. So, okay, now gain error was this term, V offset upon V full scale, 2 to the power n minus 1. And then gain error compensation is value of decimal j upon 2 to the power n minus 1 into gain error. Am I correct? So therefore, here I multiply j2 to the power n minus 1 into this term. This term left side will be there. The other side will be upon 2 to the power v of full scale upon 2 to the power n j into v offset 2 to the power n minus 1. Okay, which part is not correct? Oh, okay. Okay, yeah, here you say, right? Okay, yeah, correct. So gain error is V offset upon V full scale into 2 to the power n minus 1. And this is okay, fine, yeah. Yes, 2 to the power n minus 1. Correct. These two will get cancelled. This is j V offset upon 2 to the power n, right? And here also we have for error, we have j V offset 2 to the power n. Yeah, correct. So eventually it will be yeah, correct. Actually this also should be negative. This term is negative, should be negative. Because we have already a positive error, therefore to compensate we need to add negative gain error. Now these two will get cancelled. Negative into negative, positive, and this is negative j upon 2 to the power n into V offset. Means that when we want to correct, because now what will happen, because it is an inverting amplifier, we'll get more at the output. So gain is more. Now we will reduce it. Therefore we will have a negative. Is it correct? Any question? I think that now it's correct. Okay, that was a very, important result. It's okay. We spent some time, but it is proven. At least now you will be able to get proper. Now you can, when you simulate, now really you will see. Now having a, for example, artificial offset, then putting these phases and then compensate for the offset. Now go for the conversion cycle, and then you will plot, you will see the gain error. So this is same thing that which is shown by the theory. I had one more thing, but I think we don't have time for that. Effect of offset voltage after compensation also we discussed. Yeah, star ADC using parallel charge-based DAC. Okay, so we will come back to ADC from next lecture.